starting the recording first. All right, so this is GM week. We're not going to give you a whole lot of extra work, but we are going to give you work. We're going to do a regular week. We had last week kind of as a get caught up, get started on our projects week. And today we're going to start with another section. And like I mentioned, I had this all working last week, and then I managed to start up the lesson on virtualization, and I needed to install some new software, including upgrading WSL2. And now we are in a situation where I am no longer sure that everything is working. So we will get through as much as we can today, and then we will go on. One thing that I do want to bring out, just in case you're wondering about it, we do have some projects that are going today. These are interim reports. You can use, all I want is a couple of sheets, a couple of slides on what your current status is, and we are not expecting your current status to be, something incredibly detailed yet, but we do want you to start having some stuff. And let me see. Let me bring up presenting slides and lecture slides, and let's get to that window. Okay, so here's the list of students I have. Hong J8. Zach is going in place of Hong J8. Is it the same project, Zach? Okay, well, hopefully this is the same project, but it doesn't matter too much. We're just going to do a quick couple-minute tour through everything. The goal mainly is to make sure that you all have a project and that you're all working on a project. And we'll do this over the next couple of days until we get everybody kind of worked out. It is good, for these, it's good for everybody to be here to kind of see what's going on. I will try to save about half an hour at the end of the presentation, at the end of the class, to get through this material. All right, so hopefully you guys had a nice relaxing couple of days last week. Hopefully you're about ready to move on, and you're eager to get started. Let's go here. I think this is where we want to be next. Yeah. All right, so let's start our class today. Why? Everything is being difficult today. I don't know why. Oh, I know why. I'm in the wrong window. The problem is the window that I present in so that you guys can see everything, and the window that I actually click in so I can click in things look an awful lot the same. All right, so let's go down here. So let's start off our class today is going to be on testing and continuous integration and continuous deployment. And what we actually want to do is we want to talk about the importance of testing on an open source project. We want to talk about some integration issues. How do you pull, if you have an open source project with a lot of people working on it independently, how do you kind of pull that together and make it so that everything works in the end? How do you minimize conflict, maximize what you actually are able to get done? So with that in mind, let's start. Again, Morthy developed this. I didn't do a lot of changes, I don't think. This is going to be very important. We're going to talk about testing during this part of the lecture. We're going to talk about it in the context of Python testing, and we'll talk about it in the context of other testing as we kind of move to integration and different aspects. Your lab will do it with regard to C, C++, type of testing using C-test module from Kitware, and we'll be using GitHub all along during the integration part to kind of pull everything together. For this part of it, you guys should be familiar. If you took Python here, you should be familiar with probably DocTest. I think DocTest is the reading material we used here. Basically, it is just some documentation. It's ways to document your program so that you can actually include your testing right within your Python file, or you can have separate files. It's a nice little, if you're talking about like literal programming, it's a way to do, essentially literal testing. And UnitTest is something similar. UnitTest may have more of a JUnit kind of feel. Essentially what you're doing is you create a class, and the testing class actually imports your module, and then works, invokes it with different parameters, etc., to actually test through. Both of them are acceptable. UnitTest is maybe a little more structured. You can probably do more with it because it's more powerful in that it allows you to have this setup, specific setup routines, specific teardown routines. You can structure tests much more in the line of JUnit or other testing frameworks. But depending on what your needs are, both of these work very well, and you should be familiar with them. If you're going to do something with other unit testing frameworks, maybe UnitTest is actually better to learn because it will kind of teach you how these other frameworks are built up as well. So we're going to talk about a couple of things. The first thing is that when we're talking about testing, software is often deployed on a specific platform. So when you're testing systems, like I used to work on at GE Research, they had systems that were MRI machines. The software actually had to be deployed on the MRI machine, and actually the software had to be qualified along with the specific hardware for FDA approval. Right? You couldn't just take any software and throw it on any hardware, no matter how well the software had been tested and no matter how well the hardware had been tested. You actually had to have the two of them certified together. So testing of systems oftentimes has this implication of actually testing on a specific machine. And quite honestly, if you go into like federal government type of testing, they will specify, even if you're doing a laptop, they will specify the exact make, model of the laptop, the hard disk size, the hard disk vendor. All of these things will go together when they're specifying the system. On the other hand, most of the time, if you're a software engineer, the thing that you're most concerned with is the testing of code, and you're assuming you're running on a general processor, and you want to make sure that on a general processor your code works. So that's a software testing, and then you have a system testing, and when you put the software on the hardware, you're actually doing an integration. So why do we test? Well, first off, we test because we never write code right. That's almost assured. So we're trying to do it to do software quality control, software quality assurance. We want to be able to give some assurances, and notice this is assurance, not insurance. We want to give assurance that the software is of high quality, and we want to make sure that when we send something out the door, that it actually does generally what it's supposed to do. So software quality control and assurance. We want to make sure we build the right product. So what does this mean? We're going to want to do testing in the presence of the user, and some of our tests are going to be user interaction type tests. We could build the best software in the world. It could have all the bells and whistles. It could be extremely simple to run, but if it doesn't actually do what the customer wants, right? And customer is variously defined. It's whoever's going to be using your software. If it doesn't actually serve a purpose, maybe we paint 7 pixels blue and it works absolutely on anything, on your garage wall or something, and it absolutely works perfectly. It's the most beautiful shade of blue, but the customer wanted a database to track what's in the refrigerator, right? So you have to have this validation to actually pull out what it is you're trying to build. Does what you're trying to build meet your market needs? Does it meet the needs of, if you're quacks or yaks, does it meet the needs of the students who are trying to register? All of these are a validation step. Verification. So validation is, does it do something useful? Does it do what we want it to do? Verification is, does it do it correctly? So if we've written a specification, quacks and yaks may do a wonderful job of presenting course, classes that students can take and allowing them to pick classes. But if the classes aren't actually on the schedule, or if they're off by an hour on all the starting times of the classes, well, then they've kind of missed the specification. They're building a useful piece of software, but the useful piece of software has fatal flaws and doesn't necessarily work, or isn't necessarily useful. And finally, this possibly avoid debugging. Debugging is a pain. So once, you'll spend more time debugging than almost anything else. So one of the things we want to be able to do is we want to avoid debugging. If you write your code, if you write your tests along with your code, or if you write it before you write your code, then the whole concept is that you're going to be able to avoid debugging because you're going to test the code ahead of time. So you're not going to have lots of complicated interactions that are unpredictable or unpredicted or just plain wrong. So every unit should, every module, every piece of code should have its own set of tests. And if every piece of code has its own set of tests, you're going to get rid of a substantial number of bugs. And getting rid of a substantial number of bugs means when you get to integration, you're not going to have so many bugs to track down, and you're going to kind of lessen or minimize your debugging time. So what's the difference between debugging and testing? If one of the purposes of testing is to lower or limit debugging time, then obviously they can't be the same thing. So debugging is actually a cyclic activity. Debugging is you sit down with a known problem, you execute the code, and you try to pinpoint where the errors are and where the problem lies, and then hopefully correct them, and then you go back. Testing demonstrates correctness. So in general, if you come up with an untested problem, a problem that isn't evinced in your testing suite, you're going to spend a bunch of time replicating and debugging that problem. Replicating being the first step of debugging. Right, you have to actually be able to repeat the error in order to be able to assure that you've corrected the bug. So you're gonna replicate the error, and then you're going to correct the error, and now you're going to test to make sure that the error is gone. And what you should do at this point, and actually what you should do when you're replicating the error, is you should put together as short a piece of code as possible that actually allows you to replicate the error automatically. And then that becomes part of your testing suite. And as long as you're executing that test successfully, you know that the error is not back in. You've now corrected an incorrect code path, and you've replaced it with working code. And a test you wrote that demonstrated the failure now can become part of your actual testing suite to ensure that the problem doesn't creep back in. And problems do creep back in as people go in and modify the code or change underlying assumptions, etc. So the whole purpose of testing is to demonstrate correctness. When testing fails, then you have to go into a debug cycle to figure out why it failed and how to actually fix it. We'll talk about three different kind of levels of testing. Black box testing. I'm going to start from the bottom up. White box testing, you know all the details of the code. If you are writing new code, this is you. You should write your code based on the code structure. You should do your best to make sure that every line is executed and every salient combination of possible branches are executed. So use what you know. Use the fact that you know the edge cases, you know the assumptions you made, and put in tests to make sure that if you are going to have a divide by zero, if parameter C is 0, make sure you test for divide by 0, right? Or at least make sure you test to be sure that C is never actually entered in as a 0. Make sure that you're testing all possible paths to the best of your ability. That's white box testing. That you have intimate knowledge of the code. You're writing a test to ensure that all of your statements are correct and all of your statements are executed. Gray box is kind of one level up from that. You have some knowledge of how the system is put together. You have an idea that they're doing a sorting algorithm. But you don't necessarily know whether they're using a merge sort or a quick sort or an insertion sort. So you're not going to be able to generate tests that implicitly define explicitly exercise all of the code paths. But you do know that that they're doing a sort. So you know the basic premise of a sort. You should probably do reverse order. Put it in reverse order, see if that works. Put in a null set, make sure that it handles the null case. Put something in sorted order. Put something in. Test as many of the combinations that are salient to the operation of sorting as possible, but you're not going to go in and ensure that every line is instrumented. You want to make sure also that as you execute code with gray box testing, when you know the different Is there an issue with the audio, Hunter? All right, I'm going to continue on then. Let's So the other thing you want to do with gray box testing is you want to make sure the code correctly cleans up after itself. And I blame Nook as well. Cool. So you want to make sure the code cleans up for itself. If you're creating huge data structures, make sure that those data structures disappear when the code is gone, so that everything is working correctly. So you know some of the outside stuff that's going on, or some of the inside stuff that's going on. You don't know the exact structure of the code, but you can use your limited knowledge to make sure that everything is cleaned up and working correctly. And finally, you have black box testing. Black box testing is you got a system from Nook, and you want to make sure that there's no double echo. You have one of the specifications would say no double echo. So you want to test based on the specification, based on the test cases that the software is actually supposed to solve. Yeah, very important spec. So the idea is these are different degrees of testing, and you're going to do them at different levels. If I'm a system integrator, I'm going to treat your code, probably as black box, no more than gray box. I may have some limited knowledge of how your code is structured. Maybe you've told me the 7 modules, sloth, envy, whatever the 7 deadly modules are. So I can do some maybe limited gray box testing, but primarily I'm going to be doing black box testing based upon our agreed upon specifications to make sure that your code actually does what I think it's supposed to do and that we've agreed on. All right, where do we go from here? Okay, so that's different levels of testing. There are also kind of different kinds of tests. Smoke tests, I will tell you oftentimes when you're developing a new piece of software or when you're trying to get a new project started, that you should do a thread, right? And I would normally call a smoke test a thread test. And basically, all you're doing is you're just running through the major pathways of the code to make sure that the most critical functions work, right? So can you start up the code? Does it run? Does it produce the main screen? If you're doing a calculator, plus, minus, divide, maybe exponentiation, do you have some guarantees that here's another most crucial functions of a program work, and that's not spelled at all correctly. we should have done a smoke test on this. So smoke tests are just a limited set of testing to give you some idea that you haven't actually broken the system with your changes, that things still continue to work, at least somewhat. The second set is functional tests. This will be generally done by QA. So this would generally be you have a test plan, you have requirements, you have functional specs. So I am going to go through and I'm going to make sure that every requirement in my enormously long requirements document actually is exhibited in your code. So these will test functionality, right? So for driving a car, they'd get in the car, they wouldn't test to make sure that the fuel flow is correct, but they'll get in and they'll make sure the brakes work, they'll drive the car around, they'll check the mileage, the miles per gallon you're getting, etc. So these are two kind of high-level tests. The first is just a quick and dirty certification that something actually runs. The car starts up, it moves. The functional tests, do it meet the spec? Does it meet the spec? The unit tests, these are typically done by you. They're typically either gray or white. A lot of times they're white box testing because you can test specific aspects of the code. You know exactly how the code is implemented. You know what inputs are likely to cause execution issues, and you can actually put in very detailed tests to make this unit testing work. And finally, we have regression tests. And I'm going to be a little bit fuzzy on regression tests because I've never actually considered these to be a different form of testing. Regression tests are all of the tests you run to make sure that what used to work continues to work. So if I'm going to do a regression test suite, I'm going to have some smoke tests in there. Right? I'm going to right away start up the code. I'm going to make sure it runs. The main screen pops up. All the simple little things that are supposed to work and give the right answers. And I'm probably going to do this every time somebody makes a commit. So if you make 7 commits in an hour, these smoke tests are going to run 7 times in an hour, and they're going to be the first stage of my regression, right? They're going to tell me that whatever you've changed, the system hasn't broken completely. And then, once that's done, if we have any functional tests that have been instrumented, functional tests that I can run automatically, we will run those. And along with those, we'll run all the unit tests that we can run automatically. And we may do this once a night. We may do this once a day. Day and night. We may do this once a week. We'll do this on a less frequent basis than a continuous test. Our continuous tests are going to be limited by how much time we actually have to testing. If we're doing a new check-in every 7 seconds, well, our continuous testing is going to have to take less than 7 seconds. Otherwise, we're going to be having an increasing queue of initial tests. But the regression tests, those will run once a day, maybe every 3 hours, on some schedule that allows us to thoroughly test as much of the system as we have instrumented so that we can figure out, all the changes made in some small time period, maybe a day, maybe a week, haven't resulted in any loss of functionality. So if you've done testing, or if you've done, somebody's come up to you and found an error, and you've gone through your due diligence in fixing that error by first replicating it, and then writing a test to replicate it, and then fixing it so your test now passes, that new test should become part of your regression, because that's now something that you have written, you've put effort into this, and you can just add it to your testing system and automatically ensure that your regressions keep working. Okay, any questions? Okay, a lot of talking on this one. I'm kind of passionate about testing. When I was working at GE, one of their major software contributions to society was they had a C-Dash and C-Test. Before C-Dash and C-Test, they had other testing dashboards. And they had these large software libraries, many of them open source, and we actually sat around and did error triage every morning from 7 till or from 9 to 11. So we would sit around a big table and look at the dashboard and make sure that all of the regressions were continuing to work. And it was very effective in controlling errors and making the software of high quality. So what do we mean by high quality, and why do we want to write and do unit tests? Well, if I'm a developer, and maybe I'm working with you, and you're a developer, and I write unit tests for my code, one, I'm going to be more confident that when I pass it off to you, that any errors we find are going to be either yours or a misunderstanding between the two of us. And those unit tests are going to communicate to you my understanding of what the code was supposed to do. So we can look at the unit test as a documentation of my understanding of our agreement. So it increases developer confidence. Unit tests avoid regression. So if you're running your unit tests on a periodic basis, you know that as long as that test continues to run, you have fairly high confidence that your unit test is still producing the expected output, regardless of underlying changes to the system. Also, when it stops working, and it will eventually stop working if you continue developing on the library long enough, you know when something has had an effect that you weren't expecting, because your code is going to break. And then you actually know what time frame to look in, where to look in, and you can get it out of the way before you have 7 million of these little errors that have crept in that no one knows when or what they used to do, and you can't correct them. I like this third one. If you write tests first, you know when you are done. If you write a test that covers what the code is supposed to do, and you do it thoroughly enough, then as soon as the test passes, then you know you're done. You've actually written the code that you were supposed to write. Now, I will say that this is normally an iterative process, and your understanding of the code when you first start is not the same as your understanding of the code when you finished writing it. But as long as you iterate on these and continue to update your tests as you gain more insight into what your code is supposed to do, this holds true. And then encourage maximum modularity and minimal interface. So in other words, if you have a unit test and the unit test tests a module, that module is now separable from the rest of the system because you have a nice encapsulated understanding of how to set up and use it and what it actually does. When to write unit tests. This is kind of dumb because you write unit tests always write unit tests. But specifically, test-driven development essentially says you write the test first and then you write the code that goes along with it. And I'll buy that. That's probably the right way to do it. But maybe you just write part of the test first while you're still trying to figure out what the code does. Or maybe you just write the framework that calls your code. So you write the tests. Certainly, if you haven't written it before you check it into the repository, you should check it into the repository with a test. Almost all mature and well-structured program open source projects will require that you provide testing along with any new feature you put in. If you refactor, right, so you're going to take code that used to work or mostly worked, and you're going to want to change it so that it's simpler, easier to maintain, and maybe add additional functionality. Well, before you do that, you're going to want to know that you've captured what the system used to do, so that when you're done with the refactoring, you can go back and check and make sure that the test still works. So before you do refactoring, you should make sure you have unit tests. You should have tests for everything. And then after you're done refactoring, after you've verified the code still works, you're going to want to write stuff in your little white box world that better tests this new section of this new code features based on your intimate understanding of what the code actually does. And then again, before debugging, if you find an error that's not covered by the existing testing, write a test that demonstrates the error, and it makes it a lot easier to know when you've actually captured the error. All right. So we've been talking, and I've been saying errors and bugs and a bunch of different words. An error is made by you or I, right? An error is a mistake that makes it into the code. A fault is the manifestation of the error. So I may put in a divide by zero, that's my bad. The fault would be when the system executes that divide by zero and the program crashes. I'm sorry. An error, I would write the code that says it. The fault would be the manifestation of that. It would be in the module itself. The failure is when it actually throws the exception. And testing, right, the only way we find these exceptions, these failures, is by testing the code to try to force the failures to occur. So testing attempts to discover failures in software systems, and debugging associates failures with faults. So by debugging, we try to find where the error occurs and find out what part of the code, what sequence of actions resulted in the failure, right? Once we found that fault, we want to correct the fault, right? That's the final part of debugging, is we correct the fault so that the failure can no longer occur. And then we run our tests, and all the tests pass, and because all the tests, the system no longer has any faults, right? Yeah, absolutely not. There have been some studies, and I may have said this before. I should actually look up the studies again. It's been a while since I've read them. But there are studies that show that the more faults you find, the more bugs you fix during the development process, the fewer bugs, the better quality of code is out there. So when you're developing code, it's always tempting to say, I write good code, therefore I don't have to do as much testing, I don't have to do as much debugging. And that is absolutely false, because any sufficiently complex piece of code is going to have faults that we just didn't find. They can be hidden in portions of code that rarely get executed. Sometimes one fault will mask another fault. If the code is sufficiently complex, we can't test everything. However, regardless of how well written the code is, the more stuff you find, and this was the theme of this paper, no matter how well written your code is or how poorly written your code is, the biggest indicator of code quality was how many bugs you found during the testing phase. So the higher the number of bugs you found, the higher the perceived quality of the software was by the users when they actually used it. So testing isn't a panacea. It doesn't ensure that everything works, but the more tests we have and the more tests that pass, the higher our confidence that our system has high quality and very few bugs will be found by our users during the normal course of effort, particularly if we take each one of those reported issues, create a test that replicates it, use our debug process to get that test to pass, and then incorporate that new test in our testing suite. So when we're looking for faults, the input-output space of any software system is vast. Tests sample that behavior, looking for failures. So what we're looking for, we partition the space into equivalent behaviors, a sample each partition. What does this mean? Well, we'll look at the input-output space. We'll look at the normal processing space. We'll look at edge cases. We'll look at particularly nasty inputs or particularly inputs that don't make sense for our system. And if we incorporate all of these into tests, we have a good sampling of our space that allows us to have high confidence. So let's just take this little GCD algorithm. This is Euclid's algorithm, I believe. Basically, it says that there's a little true loop here, right? It keeps repeating itself. I've normally seen this as a recursive, but that's okay. Forever, if A is 0, then your greatest common denominator is B, because 0 divided by anything is 0. If A isn't 0, set B to be B modulo A. If B equals 0, well then A divided into B correctly, so you return A. Otherwise, you reset A to be A modulo B and start all the way over again in the top of your loop, right? Checking for A equals 0. So eventually you'll march down and you will find the greatest common denominator. What do we have to think about here? Well, what are our assumptions? So we're assuming that A and B are non-negative integers. Does this work for negative integers? I don't know. We would have to test it and find out. I think what happens with negative integers is the modulo works kind of weird for negative numbers. So we'd have to work through this and make sure that it still works. We should be trying it, right? We should know whether it works for negative numbers. And if it doesn't work for negative numbers, then we should be testing to make sure that negative numbers never make it into this module. We need to think about what assumptions about the data are implemented in the program. We should run some test cases. The first couple of test cases are just kind of the normal space. One has A be the bigger number. The second one has B be the bigger number. And actually those are, GCDs come out really quickly. We should look at prime numbers. We should look at what happens when one of our numbers going in is 0. And then we should figure out, what happens when we hit something that is not expected but is not prohibited by the rest of the code. What happens when we do negative numbers. When we think about test coverage, we want to make sure we cover all the paths. We want to cover all the loops and conditionals, right? This is white box testing. We want to make sure that every statement has been executed. We want to make sure that every branch, every if statement, every exception has been executed at least once. And if we can, right, and this is where it starts getting complicated. If we can, we want to make sure that all combinations of conditions have been covered. So that, for example, if only one path down a bunch of if statements results in an error, we want to make sure that we've covered all of those different paths. Don't know why this isn't showing. That is not going to help. Ah, there it is, yeah. So this is just a control graph. So I don't think this doesn't actually correspond to the GCD, but it is just a control graph. And if you divide your code up into different segments, this one would be a looping structure, right? Because you come down, you get down to this path, and you pop back up to your to the start of the loop. You have a branch out. This would be when the loop terminates. This would be the body of the loop. Here you have an if statement, right? If the if is true, you exit the loop to statements 4. These are statements 2. If it's false, you continue on. So now you have a branching structure and a looping structure, and you can represent all of these with a graph, and our job is to make sure that at least every one of these states is reached, at least every one of these transitions is reached, and it would be really great in more complicated graphs to make sure that every possible combination of paths are reached. So instead of just going here to here, we would want to come down and do all the way around and then out to here, right? And just make sure that everything is tested every time. Any questions? Well, that's not showing. I'll have to take a look at it. In the interests of getting through integration, which I would really like to get through today, we're not going to do this in-class exercise, but I want you to think about it. Write the input-output specification for a binary search. What are we going to need? Well, for input, right, we're going to at least need to know the number we're searching for. We're going to have some type of list structure. for our binary search to operate on. If it's a binary search, that list structure has to be in a sorted order, right? Our functional spec would say something along the lines of search takes in a sorted list as parameter 1 and a number in parameter 2. And if you're doing a normal binary search, it would say it returns either the location of X in the sorted list or the insertion point of X if it is not, where you would insert it in the list if it's not there. And then for tests, we'd want to test a bunch of things, right? We would at least want to, and I would generally we would be doing this in an open discussion. So if you want to type anything into the chat, please do so. But the whole idea would be we would want to test it with a list of 0 entries. We would want to test it with a list of more than 0 entries. We would want to test it where the insertion point should be before the list, where the insertion point should be at the end of the list, where the insertion point should be in the middle of the list, and we'll want to test it with entries that are and that aren't there, right? So we want to be able to find it. We want to be able to not find it. And then maybe we want to play around with the list itself. Maybe we want to have duplicates, right? What happens with duplicates? Do we return the first value or the last value or any arbitrary value? So these are, kind of the things that we want to look at if we're going to write tests and if we're going to try to figure out how to test something like a binary search. We're going to want to test things in the first half of the list. We're going to want to test things in the second half of the list, just to make sure that we're forcing both loops on our list, that we're not always just testing things that are inserted near the front or that are found near the front, things that are found near the back. We're going to probably want to test lists of length exactly 1, because sometimes lists of length exactly 1 can result in errors as well. So, in just this simple little binary search, we've come up with a lot of specifications, and maybe I could probably get about 10 or 15 tests out of just what we've discussed so far. Okay, we covered C-test before, kind of, when we talked about build systems. We're going to look at, we gave you some documentation on UnitTest and DocTest. If you do for Python, there's also a PyUnit, just like there's a JUnit for Java. So there are a lot of language support for testing. There's a lot we can do with it. Let's just do a quick little exercise. Again, I'm trying to get to integration. Maybe we'll have to run a little bit of this at the start of our lab on Tuesday, but I don't think the lab is all that bad. Then again, I just made it longer, so yeah, I got rid of one thing and did another. So let's look at some code. Test UnitTest.py, right? We're going to look at a code called test. Well, I'll tell you what. I'm just going to pull these up. I've got them in my Ubuntu window. So let's see. We want to take a look at not able to change the font right now. Okay, so we have this this code here. This is my Ubuntu window. We want to look at a unit test thing. So let's look at we'll look at unnecessary math.py first. This is some math that we don't necessarily have to do. It's just a multiply routine. But we're going to embed some stuff in here. If you've used doc tests before, you know that these three greater than signs specify something that's supposed to be executed on the command line by Python. and then the thing following it is the answer that's supposed to be returned by Python when you do this. So what we're doing is we're specifying two tests. We're multiplying 4 by 3, and we're multiplying a by 3, and we're giving two answers, 12 and a there. This is just in the comments. You'll notice that the three quote marks, right, denote this as a multi-line comment. So this is not actually executable code, except when we're doing the doc test tests. The return from that then is just the actual multiply operator, a times b. We can also look at test unnecessary math. And what we'll see here is this is pretty much exactly the same thing, right? This is just the multiply commands, and I'm going to make this just to differentiate. So that we see what's actually happening when we run the tests, right? So this is just a text file, but it specifies the same executable lines and then answer lines as our other, as we're embedded in our comments for our modules. And then, of course, we can have test UM. So that was using doc test, and we can do test UM unit test.py. And what that does is it imports this unit test class, and then it sets up a unit test in our unnecessary math, right? We import the multiply from the unnecessary math, and then we can set up this class that has some setup code, and I believe it also has some teardown code where we can define stuff that allows us to make our tests easier if we have to initialize variables or anything like that. And then it has a bunch of things that start with test underscore that are the tests we're actually going to execute, along with specifically coded in values that we're looking for. So a times 4 would be 4 A's, and 5 times 4 should be 20. Okay, and from these we can actually execute a bunch of different tests just to test our Python. And this next couple of pages just shows what we had there. I guess I could have done that right from here. So let me go on to what we're actually running these. The test unnecessary math.python, the last one we did, that's a unit test. So we can just run that normally. So we can say something like Python test unnecessary math test, and it tells us it ran 2 tests in 0 seconds. And we got an OK because they all passed. Is there a -v flag on that? Yeah. So we can run -v, right? And that's showing us all the steps, including the cleanups, the clears, all the imports that get imported for running the tests. And it still tells us ran 2 tests in a slightly longer amount of time. So that's what you get back when things actually work. That's the unit test framework. Again, all you do is you write your unit test file, and then you execute it. And you can do this, in any suite of tests, any system that's able to run your tests. CMake we use for C++ to run all these, but you can also just have a batch file that runs through and runs everything. And then we can look at 2 different ways to run our doc tests. The first is we can do a doc test. Wow, how far back did I have to go? Right, we can run our unnecessary math, or we can do -doc test. -v unnecessary math, and that did not work. -m doc test. One final time, right? And that'll run the doc tests that are embedded in our unnecessary math file, right? Again, that was just the implementation itself, right? That was this one, but we can also run that on our text file and get the same results. So what this allows us to do, and let's see, I had a failure because, oh, I didn't change the expected output for any of these. So we can come back in and change those. Got to change the answers when you change the tests. Okay, and now we actually get the correct results and everything passes. All right, so that's just a little bit on some testing, some tools for doing unit tests in Python, for example. All right, any questions? We're back up in our testing world. All of that is kind of documented here. And that's basically, why we want to do testing and some quick Python tools using UnitTest and DocTest to actually run the testing. All right. Whew, a lot of talking there. I've got about 25 minutes. I'm not sure.